Good morning, dear students. Today we are going to discuss calibration curves, and this is something I need to repeat because in the last lecture there was some problem with the mic. So pay attention to the last topic of this chapter, chapter number 2, calibration curves. The term indicates that we are plotting a graph actually. Curve refers to graphs. So they could be a straight line, they could be a curve, but even a straight line is referred to as curve on the calibration curve. So in calibration, we study one quantity in relation to another. The act of marking on a scale. Like if this is a thermometer scale with the 0 degrees Celsius here, let's say this is 0 degrees Celsius, and then this is 1, 2, 3, 4, and this is 5. That means this is the size of the division. This is the size of the division of 1 centigrade scale, and this is exactly 1/2 of centigrade scale. But how did we decide that this should be the size of exactly 1 degree Celsius, 1 degree centigrade of the temperature? For this, I take you back to O-level classes. If you remember, we used to study theta, to study how the length of the mercury column is varying as we increase the temperature. The graph that we obtained as a result of this study was something like this. It is starting from a non-zero value here. This means this is the length of the mercury column already when the temperature was 0. So at 0 degrees Celsius, this was the length of the mercury column. But we are interested in the subsequent changes in the length of the mercury column, how it expands with the increase in temperature. So we make this increase. This is 20, this is 30, this is 40, and so on. And this is the subsequent change from this L0 upward. So this is the change that corresponds to the change in temperature. 10 degrees Celsius temperature has caused an increase in length by this amount. But is it the same increase in the next 10 degrees Celsius? I mean, in the next interval, what is the change in length? And we observe that it is the same increase in length again. This means the change is linear. So on a linear scale, the size of each division is exactly same on linear scale. So I get exactly the size in centimeters of the length by which the mercury column has increased. So this is, let's say this is 0.5 centimeter or 0.6 centimeter, whatever it comes out to be. It is actually based on a graph which was the graph between the temperature and the length of the mercury column. So any such study which leads to our understanding of how much should be the length of the division and whether this scale is linear or non-linear. I'm coming to an example of non-linear scale shortly. But on a linear scale, we know that all the changes, subsequent changes with temperature will take place by the same amount. So that is why the line. So that means this is a general term. This curve could be a straight line. It could be a curve downward. It could be a curve upward. So let's have a look at an example of non-linear change. Suppose in another type of thermometer, we are studying the change in resistance with temperature. Suppose with degree Celsius, this resistance in ohms is studied, and we find that for a certain material, because material behave in different ways, for a certain material, the resistance with temperature increases in this manner. At 0 degrees Celsius, there is some resistance, but as you increase the temperature, the resistance increases like this. That means as you increase the temperature from 0 to 10, there is hardly any increase in resistance, because see, this is almost straight line. But in the next 10 degree increase in temperature, there is a slight increase observed. And in yet another 10 degree rise in temperature, the increase in resistance is more significant. So this is what we see on the graph. In the first 10, there is a very, very small increase in resistance. In the next 10, there is a slightly larger increase. Then there is still bigger increase, and so on. So the size of increase is becoming bigger and bigger in the same intervals of change in temperature. If we are asked to mark the size of the divisions on a scale like this, what should be the size initially, and what will happen to the size as we go to the higher temperature? This will help us. This side clearly helps us that initially the size of the division is very, very small. So it could be something like this. So a scale may look like this. That means during this division, the increase in 10 degree, and during the next 10 degree rise in temperature, the resistance. Now this is this type of scale in which the division of the division has smaller size in the beginning and then its size changes. This is known as non-linear scale. So on a non-linear scale, size of each division is different, but it could happen in two different ways. It could be small initially and then it increases gradually. This is what we observe here. But what if we have a situation like this? Suppose there is another type of material that we are studying with temperature, and for that particular substance, the resistance, which is initially increase, becomes smaller and smaller and smaller until it stops increasing any further. So this could be the behavior of a certain material. Now they are definitely not going to ask you the physics of this situation, what exactly happens here for this particular topic. They are only interested in how you interpret this graph in relation to the size of the division. So this time, if this is the resistance again, initially it has some value, but that is none of our concern. We are mainly concerned about what happens after 0 degrees Celsius. The resistance has changed from this value to certain higher value. So this is the size of that change for 10 degree Celsius. So if this is the size of the 10 degrees Celsius, this could be made even more sensitive if instead of 10, we make it for 5 initially. That gives us a better size of the divisions, and it could be even better if we make it for 2, let's say. So this could be could be the scale. It will look like this. So at 0 degree Celsius to, let's say, 2 degree, then to 4, then to 6, then to 8, the size of the division will go on becoming smaller. If you see, initially it is large change, but for next 5 or next 10, it will be even smaller, and then it will go on becoming very, very small, and then there will be a change in temperature corresponding to which there is hardly any change in resistance. So this is the idea of calibration curves. Calibration curves, I repeat, are used to decide what should be the size of the division on a scale, and whether the size of that division should increase or decrease. That is the main purpose behind. One last example that I discussed in the last lecture. Let me discuss that quickly. Then we move on to the next chapter, because that topic will finish. One example that I discussed was the study between the fuel in the tank. This is fuel in the tank, and this is where the tank is full. So let's say this is full F. And we are studying what happens to the angle of deflection of the pointer. This is the fuel gauge of a car, and we have a pointer which usually moves in this way. Let's say this is here initially showing that this is full. This is F here. So this scale is showing that you have your fuel tank full, and the curve that we study, it has a certain shape, and that shape is something like this. This is the shape, and this shape has obtained as a result of our study of the angle that the pointer moves when we have consumed a certain amount of fuel. This clearly indicates that the size of the divisions on this scale will not be same. As you consume the fuel, clearly you see initially the change is very, the deflection will be small initially. So you see the deflection, if you have consumed half of the fuel, see, this is exactly half of what you have consumed. But the angle through which you have moved is not exactly half of the total value. If let's say this is a 90 degree angle, so initially it was here, and it has moved exactly through 90 degree to show that it is full scale. So if this is full here, then this is 90 degree. So after you have consumed half of the fuel, the pointer has moved only through this angle. See, that means half of the fuel, for half of the fuel, your pointer will move only through this one. This is what the scale is showing. But for another half of it, I mean, if you have come here, this is what you get. For another half, it is much larger. See? So the pointer has moved a much bigger angle, and it will arrive probably here. This is what the new position is. And that means you are very close to the end of the fuel now. Now the end is this, because the fuel is should be 0, but the curve is showing that even though the angle is 0 here, the angle is 0 here through all this, the fuel is not 0. The fuel is still in the tank, because this is a non-zero value of the fuel. This is done intentionally, as I said in the last lecture. This is done intentionally to save you from any trouble, because even though this is showing 0 fuel, you may not have a refilling station around or nearby. So you have to wait for another half an hour. You have to travel a few more kilometers before you can refill your fuel. So this is to serve a useful purpose. So this was the last example that I discussed in the lecture. With this, our chapter 2 has completed. And now we move on to kinematics. Kinematics is that study of physics in which we ignore the mass of the object, we ignore the we ignore the force that is acting on the object. We are only interested in describing the motion of this object, whether this is moving with a constant velocity, whether there is an acceleration, or that acceleration is constant or variable acceleration, whether the object has come to a rest for a few moments and then started again. So all these changes in its motion are studied with the help of some principles discussed in this chapter, kinematics. So kinematics is about motion and how we describe it. This chapter starts with the discussion of distance versus displacement. Distance is the actual length of the path that we follow when we move from one point A to another point B. It could be any path we have taken. It could be a path starting from A, going all the way to B, taking several turns in it. So when we measure it carefully to, let's say, a millimeter, we can say that we have traveled this distance. And if we have followed a path like this, we have obviously traveled slightly longer distance, because maybe we have a problem on this path. This was the only available choice, a better choice in a given situation. So this is the length of the path that we have traveled now. So this is distance. So distance is the length of the path we have traveled. But displacement is the possible distance which is shortest from your initial position to another. So displacement from A to B is the shortest possible distance which is directed from initial position to final position. These definitions are given in all physics books, so I'm not writing the definitions, I'm just saying it, I'm speaking it, so you get the sense of it. So one difference is obvious, that displacement is has one value and it has a direction. It is shortest possible path of the length. It cannot be smaller than this, and there is a direction attached to it. With distance, we have several choices. You can take any road, any turn, any number of steps you can take, and there is no direction attached to it. So for this reason, distance is always a positive quantity. Always a positive quantity. Whereas displacement could be positive or negative. If you go from A to B, you have moved, suppose, 2 meters. But if you have moved from B to A, you have moved minus 2 meters. So for this reason, distance is not zero in a closed path. In a closed path. So if you have started from point A and you have moved any length, but you have come back to the same initial position, you have moved in a closed path, distance is not zero, but displacement is zero. Zero for a closed path. For this reason, average speed is never a zero, never zero. Average speed is never zero. Average speed is never zero. If you have moved some distance, you divide by some time, there will be an average speed which is not a zero quantity, which is not zero because you have moved some distance, but average velocity may be zero. Average velocity may be zero, and the example is closed path. If you have taken this displacement, you have moved from A to B, you have come back to A again, you have taken the average displacement, that is zero, because you have added algebraically divided by the time it has taken, so it may be zero. The average velocity may be zero. Average displacement may be zero. This is obviously a scalar quantity. Distance, there is no direction associated, so scalar quantity. And this is a vector quantity because it is it has a sense of direction associated with it. So this particular part is something related to speed and velocity. So that comparison is coming next. So I quickly repeat what are the main points about distance and displacement. Distance is any length of the path you have chosen. Displacement is always fixed from A to B. As long as the points are fixed, displacement is something fixed. The only path that is shortest and it has a direction from initial to final. It is always positive, the distance. It could be positive and negative depending upon the direction you have taken. It is not zero in closed path. If you have traveled some distance from A to B and you have come back to A, the distance is of course added, but in this case it is zero. And if I skip this, because this is discussed in the next comparison when I compare speed and velocity, I come to this one, scalar. This quantity is scalar because there is no direction associated, and that one is vector. Similar comparison is between speed and velocity. Let's discuss that quickly, and with that we finish today. This is speed and this is velocity. Speed has something to do with how fast you are moving, but speed is distance divided by time. What distance you have covered divided by the time. So obviously if you have taken this path, this is path 1, your average speed will come out to be higher. But if you have taken this path 2, you have traveled slightly longer, and obviously you have taken longer time. So you come out, you will have slower, you have moved slower because this is longer distance. But in all these two cases, the displacement has remained the same. So speed is whatever distance you have traveled divided by the time you have taken. But velocity means while you are moving on this path or on this path, your vector was developing, and what is the rate at which this developed? So while you are moving here, your vector was developing here. So if you have moved from this to this in a certain time, you divide all that distance divided by time to get the average speed, but you divide this distance, the displacement, divided by the same time to get your velocity. So speed and velocity are very different quantities here, as we can see from this example. Speed is always a positive quantity. Velocity could be positive or negative, because in one direction it may have one sign. When it changes direction, it has the opposite sign. Speed is not zero, and here we can take this example. Average speed is never zero, because if we have moved in a closed path, even the distance is not zero because it adds up. So even in the closed path, average speed is not zero. However, it may be zero when you move in a closed path especially. And this is the last thing is same for speed and velocity, like it was same in scalar, and it was for distance and displacement. This is scalar, this is vector. One definition that we could add here is that of acceleration. Acceleration is the rate of change of velocity with respect to time. But usually this is understood that rate of change of velocity is with respect to time. So with respect to time, or time rate of change of velocity is written without the word time here. The word rate of change basically means the change in velocity divided by time. So basically this is time rate of change, but this word time is usually skipped here because that is considered understood. V minus u means this is the final velocity, this is initial velocity, and this is the total time in which this change has taken place. So this is usually written as delta V over delta t. Sometimes it is written in this way. In your books, sometimes you see this, this symbol. This is delta, which shows change in speed. This is change in time. So delta is the symbol used to show any change in a quantity. So this quantity, which is known as acceleration, this is usually denoted by small a. That means this small a is related to initial and final velocity and the time taken during which this change has taken place through this equation. And this is going to be our starting point in the next lecture. When I rearrange these terms, it becomes V is equal to U plus AT. When you rearrange this, obviously you multiply it by this, it becomes AT. So V minus U is equal to AT, and then you bring U to this side to make it positive. V becomes U plus AT. This is equation 1. We'll refer to it as first equation of motion. This equation will be applicable in all those situations in which we have some idea of what the initial velocity of the object is, for how much time it has moved with a certain constant acceleration to acquire the final velocity V. So this equation will be used in certain situations, but we have few other equations of motion, and that we'll discuss in the next lecture. We'll start from this point next lecture. Thank you for today.